Okay, so let me know.
So not you, the person who will introduce you.
Okay.
Hello, Nazneen. Yes, please.
Good evening and welcome back. We are going to start the 18th technical talk of the workshop. In this session, we are going to introduce our 8th speaker of the workshop. We are honored to have Dr. Shane Farnsworth as our speaker. Dr. Shane Farnsworth is a junior researcher currently based at the Max Planck Institute for Gravitational Physics in Potsdam, Germany. He has been there for the past 5 years. Prior to that, he did his PhD at the Perimeter Institute for Theoretical Physics in Waterloo, Canada. His research interest includes studies on particle theory, early universe cosmology, etc. He has a number of publications in highly reputed journals like Physical Review, The Physical Review, etc. We are very much happy to have you here, sir. Before handing over the session to Dr. Shane Farnsworth, I would like to request all the participants to kindly turn off your camera and mic, and if you have any questions, kindly put them in the chat box. Over to you, sir. Thank you.
All right, thank you very much for that introduction. Thank you to all the students who are here to sit through my lecture, and thank you also to the organizers for this kind invitation. It gives me a really nice opportunity to talk about some ideas that I find really beautiful and I've been interested in for some time. They're not directly related with my research, but I think they're beautiful enough, and I hope the students will also find them useful. So I'm going to be talking about Dinkin diagrams and their application in high-energy physics. So Dinkin diagrams are a tool which allows you to analyze large Lie algebras. But before jumping into that, I just want to mention one or two quick points. So I realize this lecture is coming somewhat late along in the workshop. So there's some possibility that there will be some overlap between what I'm going to be saying and what some previous speakers have covered. And I don't think that's a big problem. I think you should see this lecture as an opportunity to really hone your understanding of some of these ideas. Because some of these ideas will pop up again and again in your research careers. And yeah, so the approach I'm going to be taking is I'm going to provide no formal proofs. I'm going to be relying, for the most part, on examples. And so I'm hoping this will give you a real hands-on feel for some of these ideas that I'm going to be introducing. And I hope that also makes this lecture accessible for people who weren't part of all of the workshop talks up until this point, if you miss anything. Okay, so with that being said, if you have any questions and you want to ask them immediately, I've also booked enough time so that if you want to stop me, I'm also very happy for anyone to turn on their mic and ask a question directly if they'd like to stop me at any point. Okay, so in any case, let me begin. So why Dinkin diagrams? Right? So usually when students are first introduced to Lie algebras, it's done through some simple examples. So for example, SU2, SU3, SO4, some of the smaller Lie algebras. And what that means in general is that you start by playing around by brute force, right? You can usually just through computation work out things like the commutation relations or the structure constants. You can work out subalgebras. You can work out, you can explicitly construct representations for these very simple and small Lie algebras. And that might give you the impression that you don't really need any sophisticated tools to play around and analyze Lie algebras. But that's not really the case. If you're interested in physical applications, then quite quickly you run into larger Lie algebras where things become fairly unmanageable. Right? So if you're playing around with higher dimensional theories or grain unified theories, then you'll often run into larger groups like the larger exceptional groups, SO10, and so on. And so it's good to have some nice tools at your disposal to do some of the analysis. So just to give you an example, consider the exceptional Lie algebra E8. So this is a 248-dimensional Lie algebra. And if you do a Google search for this algebra, what you'll find almost immediately at the top of your search will be some images that look very similar to what you see on the screen now. I know that's what you'll find because this is where I found this figure. And so what this is a two-dimensional projection of some higher dimensional object, right? So two-dimensional graphical depiction of E8, this very large object. Right? And this visualization, of course, is extraordinarily pretty. It's colorful and nice, but it's not very informative. It doesn't really help you if you want to play around and actually know what E8 is. Right? So what Dinkin did, and what's nice about what Dinkin did, is he worked out a way of containing of expressing all of the structural information about a Lie algebra in some very simple two-dimensional diagrams that are now called Dinkin diagrams. Right, so this is the Dinkin diagram for E8, and it's not as pretty as the previous visualization, but conceptually it's much more beautiful because it contains all the information that you need about this Lie algebra. And not only that, but there are some techniques which you can use for finding subalgebras from the Dinkin diagram directly. Right, so what I want to do today and tomorrow is I want to give you a real hands-on view of Dinkin diagrams and their application in high-energy physics. And I want to give you enough tools that you can go ahead and read essentially any review or paper which deals with these tools. Okay. So that being said, let's begin. And I'm going to begin with a little bit of a brief review of some of the objects that Lie algebras, that Dinkin diagrams rather describe. So I'm going to give a quick review of Lie algebras and the groups they generate, as well as a brief discussion on representations. And I know that everyone here has been sitting through a week of workshop, and so you're very familiar, I suppose, with these notions. But it can't hurt to bring us all up to speed and make sure that we're all happy with the notation I'm going to be using throughout the talk. So to start with, an algebra is just a vector space equipped with a product. And Lie algebras are no different. So Lie algebra is going to be a vector space defined over some field, F, which is equipped with a bilinear product. And the bilinear product satisfies the following properties. So it's, first of all, anti-symmetric. And that means if you take any two elements of the algebra, A and B, and you multiply them together, then A times B plus B times A is equal to 0. Right? That's anti-symmetric. Secondly, any Lie algebra will satisfy the Jacobi identity. And you can view the Jacobi identity as encoding the associative properties of the algebra. It tells you about how associative the algebra is in some sense. Right? So all of the Lie algebras that we're going to be interested in, they'll be satisfying this property here. And we're always going to be looking at algebras over the complex numbers or the real numbers. Okay, so that's Lie algebras. That's all I'm going to say in review. But some important words are going to pop up throughout the remainder of the talk. So just to get them out of the way, when I say the dimension of a Lie algebra, what I mean by that is the number of linearly independent basis elements, right, of your Lie algebra. When I say rank, what I mean by that is the maximal number of commuting basis elements in an algebra. So if you take your algebra and you can select some subalgebra of commuting elements, and the maximal subalgebra of commuting elements, the dimension of that subalgebra will be the rank of the algebra. So the rank, you can think of it as the maximal number of simultaneously diagonalizable basis elements. Okay, I'm going to be dealing almost exclusively with simple algebras. So simple algebra is a non-commuting algebra, or you might hear some people say non-abelian Lie algebra, that doesn't contain any proper ideals. Right? So a proper ideal is a subset of the algebra which is closed under the action of any element in the algebra. Right? So if our algebra doesn't contain any such sets, then it's said to be simple. Okay? And if we take the direct sum of simple algebras, we get semi-simple algebras. Okay? So there's just some definitions there. If anyone, if that's not clear to anyone in the chat, then please stop me now and get me to explain anything you're confused with, because these definitions will pop up again and again. All right, so Lie algebra. So I'm just going to give some very basic examples that I'm sure you've seen over the previous week, but just to bring us all up to speed. So the archetypal, the most common example that's usually given is Su2. So this is an example of a three-dimensional rank 1 simple Lie algebra. So it's three-dimensional, which means it has three generating elements, the Ti's, and they obey this multiplication here, this product. And you can see immediately, since these epsilons are antisymmetric in all of their indices, you can see that this product will obey the antisymmetry property for Lie algebras. And if you go ahead and check, you can see that this product will also satisfy the Jacobi identity. And if you haven't seen that before, I highly recommend you go ahead and check that for yourselves. It's quite an informative process. Okay, another example, which again, I'm sure you're all familiar with, is Su3. So this is an 8-dimensional rank 2 simple Lie algebra. Being 8-dimensional, it has 8 generators, the Ti's, and they follow the following multiplication rule. Ignore that epsilon there, that's just a mistake at the front of the structure constant. But anyway, they have the following product rule where the Fijk's are structure constants with values given down the bottom. And they're once again completely antisymmetric, and you can check for yourself that this product satisfies all the properties required for a Lie algebra. Okay, so that's all I'm going to say in review of Lie algebras. Next thing I want to talk about is Lie groups. And so you might be wondering, why am I talking about Lie algebras if this is a workshop on symmetries? And the answer is that there's a correspondence between Lie groups and Lie algebras. And this is a correspondence that I often see people confused by even late into their careers. So I'll just go over it quickly again here. So for the particular Lie groups that we're interested in, you can think of their group elements as being generated through exponentiation of Lie algebra elements. Right? So in other words, if I have some element U, which is an element of my group G, then I can express it as the exponential of some C, where C is the element of a Lie algebra. Okay? And for the groups that we're interested in this talk, you can think of this exponential in terms of a series expansion. You might call it the matrix exponential. And in this case, the group operation is just given by a multiplication of two exponentials. So EA times EB is equal to EC, where C is given by the Baker-Campbell-Hausdorff formula. Now, I know earlier in the workshop, one of the presenters has already taken you through the Baker-Campbell-Hausdorff formula. So I'm not going to go into too much detail here. I'll just mention 2 points which are quite interesting. The first point is that you can actually determine the form of this expression for yourselves by brute force, and I recommend for you to do that if you haven't done it yourselves. So for each of these exponentials, you can write them out in this series expansion, and then just turn the handle, turn the crank, and brute force calculate and determine what the form of this series expansion should be. You can do that for yourselves if you're interested. But secondly, and perhaps more importantly, if you have a look at the form of the Baker-Campbell-Hausdorff formula, it takes elements in the Lie algebra, these A's and B's, right, and it adds them together, and it multiplies them using this commutator, this Lie product. Right? So a Lie algebra, being a vector space, is closed under the sum, and it's also closed under the Lie product. And because of the form of the Baker-Campbell-Hausdorff formula, you're more or less guaranteed that C will be closed in the algebra, and as a result, this product will be closed in the group. Right? So the closure of the group operation derives from the closure of the Lie algebra operations. Okay. So just to finish up on groups, all of the finite dimensional, compact, simple Lie groups have been classified. And so I'll just go through this classification really quickly. There are the special orthogonal groups, denoted SON. These are generated, you can think of them as being generated by the Lie algebras of real n by n anti-symmetric matrices. And applications that you'll often see is the special orthogonal groups often pop up when you're discussing rotations in space. Right? So you would have seen SO3, for example, in rotations in 3 dimensions. The special unitary groups, these are denoted SUN, and you can think of them as being generated by the Lie algebras of n by n complex anti-Hermitian matrices. And applications-wise, you often see these popping up in high-energy physics, for example, as gauge groups. Right? These you often see as the gauge symmetry of some particle theory. In the standard model, for example, the symmetry group is SU3 cross SU2 cross U1. Thirdly, there are the symplectic groups. So you can think of these as being generated by the Lie algebra of 2n by 2n matrices of the following form, right, where B and C are symmetric. Applications-wise, you often see symplectic groups popping up in quantum mechanics. And finally, so those are 3 infinite families. And finally, there are the exceptional groups. There's 5 of those: G2, F4, E6, E7, and E8. And these are generated by the exceptional Lie algebras that share the same names. So you might see these in high dimensional spaces, theories in such as string theory, or you might see them in grand unified theories as well. G2 is quite special. This is the automorphism group of the octonions, or the symmetry group of the octonions. F4 is the symmetry group of what's known as the exceptional Jordan algebra. E6 is the symmetry group of what's known as a Brown algebra. E7, I'm not sure what that's the symmetry of. I don't have a nice example for you there. And E8 is the symmetry group of itself. All right, so that's all I want to say about Lie groups and their classification. I hope that's all content that you've seen to some extent over the past week. So now I just want to talk briefly about representations before jumping into the real content of the talk. So usually when physicists learn about Lie algebras, they learn about them in terms of representations. So what's a representation? If I have some Lie algebra, some abstract object, then what I can do is I can find a representation of that algebra as operators on some vector space. Right? So you can think of a representation as a way of expressing your abstract object in some tangible way. It's a representation is a Lie, it's a map, it's a Lie homomorphism from my basis elements in my algebra to operators on some vector space. And you ask that the representation of an algebra satisfy all of the properties of the algebra itself. And that's this Lie homomorphism property. Right? So in equation 7, what this equation is saying is that if I take 2 elements of my algebra, A, B, and I multiply them together and then form their representation, that should be the same as forming the representation of my algebra first, of both my elements, and then taking the product. Right? So usually you can think of these as being represented as matrices, and in which case on this side, this bracket would just be the commutator of matrices, and over here, the bracket here would be the Lie product of the algebra. Okay. And so all that being said, just think of a representation of a Lie algebra in terms of matrices acting on some vector space phi. Okay, so I'm just going to give one example of a particularly important type of representation, and it's known as the adjoint representation. I want to just mention this briefly because a lot of people find this can be quite a confusing issue. So every Lie algebra has what's known as an adjoint representation, and that's the representation of the algebra on itself. So at the start of the talk, I told you that an algebra is just a vector space equipped with a product. So what you can do is you can represent a Lie algebra on that vector space, right, by making use of the Lie product. Right? So for example, if I have some algebra element A and some vector element V in some vector space, then the adjoint action is given by the Lie product. Right? So in particular, since if you take an n-dimensional Lie algebra, then you can express this representation in terms of n by n matrices on n vectors, where a nice basis of generators is given by the structure constants. Okay. I'll just give some examples quickly to hammer this into your heads. So the first example I gave was the Su2 Lie algebra, and this has a nice representation on C2 as 2 by 2 matrices. Right? So we can represent the generators of our algebra as ion 2 times the Pauli matrices, where the Pauli matrices are given as follows. Right? So you're probably very familiar with this. Then there's the adjoint representation of Su2. So Su2 is a 3-dimensional algebra. So the adjoint representation can be given as 3 by 3 matrices on R3. Right? You can think of R3 as the vector space of the algebra. In which, again, the generators are given by the structure constants. Okay. So you can, in the 3-dimensional representation, you can write out a nice basis in terms of the structure constants, and here they are here. And of course, you can keep going. You can find a 4-dimensional representation of Su2 on C4 and so on. But we won't be going any further. And so the second example that I gave of a Lie algebra was Su3. So this is the 8-dimensional rank 2 Lie algebra. And you can there's a nice 3-dimensional representation. So representation in terms of 3 by 3 matrices on C3, written in terms of the Gelman matrices. And you're probably, again, very familiar with this. And as with any Lie algebra, there's an adjoint representation. So in this case, the adjoint representation is given by 8 by 8 matrices, given by, again, by the structure constants, acting on R8. Right? Since it's a real 8-dimensional matrix algebra, Lie algebra. Okay, so that's all the review that I want to do. I'm not going to go over anything else in terms of review. The next thing I want to do is start in earnest. So the whole purpose of this talk is to introduce you to some tools which will allow you to play around and analyze Lie algebras even when they get quite large. Right? And so the first step towards this is coming up with a nice basis. It always makes your life easier if you can describe things in some nice basis. And so I want to introduce what's known as the Cartenbar Basis. But I have to make mention of something first, and that is, in order to write your algebra in the Cartenbar Basis, you need to employ a trick. And that is, to this point, all of the algebras that I've introduced, or all of the finite dimensional compact simple Lie algebras that I've mentioned, they've all been real algebras, meaning they're defined over the field of real numbers. And those algebras, it's very limited the sort of bases you can construct. It turns out what you can do is you can extend these Lie algebras to be defined over the complex numbers. Right? You can complexify the real Lie algebras by tensoring by C. And then this gives you access, without changing the details of the commutation relations of the generators, it gives you access to some nicer bases that you can play with. And so that's what we're going to be doing here. think about all those real algebras that we've already mentioned. We're looking at their complexification, and then now we're going to look at a very special basis called the Cartan-Weil basis. Okay, so what is the Cartan-Weil basis? Well, the idea is very simple. You separate the basis set into two subsets. The first subset you fill with all the simultaneously commuting elements, right? So you find the maximal set of commuting basis elements, right? And they form what's known as the Cartan subalgebra, right? And so the dimension of the Cartan subalgebra will be equal to the rank of your Lie algebra that you're looking at, right? And the second set of generators you fill with what I'll call ladder operators, these E alphas, right? And you ask that they satisfy the following relation, right? So these relations here, these commutation relations, these are just the product rules for the algebra written in the Cartan-Weil basis, right? So these alphas are structure constants written in this basis. And in fact, these will all be real. These are also known as root equations, where you might see these called roots. Okay, so this is the Cartan-Weil basis. So why is this particular breakup interesting? What I'll do is I'll give an example first to give you some feel for how the Cartan subalgebra functions, to give you some idea of why it's interesting. So let's return to an example of our representation of Su2 on C2. Right? Our representation of Su2 in terms of 2 by 2 matrices acting on the two-dimensional complex vector space. You can express this vector space here, V, in terms of a nice basis, right? Which I will label suggestively by 1/2 and 1 minus half, right? Now, because Su2 is a rank 1 Lie algebra, you can choose any of its basis elements as being the Cartan subalgebra, right? Only one algebra element, one basis element will commute with itself. And it turns out that it's rather convenient to choose T3, right? If we look back in terms of, I won't do that. So it's quite convenient to choose T3. So in the two-dimensional representation, we're going to take our Cartan subalgebra element to be minus I times the two-dimensional representation T3. And it will take this form here. Now, what you'll find is these basis elements for our vector space V, they will act as eigenvectors of this Cartan subalgebra, right? And they will associated to these eigenvectors will be the eigenvalues plus or minus 1/2, right? And so what we can do is we can use these eigenvalues to label the eigenvectors. And this is why I've used this suggestive naming convention here. Okay. So let's look at another example, then I'll talk about the general case. So the three-dimensional representation of Su3 on R3, we can break up, we can express V in a nice basis, which again I'll label suggestively as 1, 0, and -1. And once again, we're free to choose which element of our algebra is the Cartan subalgebra. But again, I'll choose T3, and then I'll choose H to be the minus I times this should be the three-dimensional representation of T3. And once again, we get a diagonal matrix with eigenvalues 1, 0, and -1. Right? And so once again, what we're seeing here is these basis elements are going to act as eigenvectors of this Cartan generator, right? And associated to these eigenvectors, we have eigenvalues 1, -1, and 0. And so we can use these eigenvalues to label these basis elements of the representation space. Okay, so what's the idea? So
Professor?
Yes?
Can I ask a question?
Yeah, sure, go ahead.
In the adjoint representation of Su2 algebra, there was no diagonalized matrix. Then in this case, we have done similarity transformation and then write it here, right?
Yes, that's true. So that's a good point. I didn't mention that.
I mean, we didn't have any diagonalized matrix in the adjoint representation of the Su2.
Yeah, that's a very good point.
We have a diagonalized. We have done some kind of similarity transformation, right?
Yes, that's correct. So very good point. So if we go back and we have a look at three-dimensional representation of, sorry, who was it that said that? What's your name? Sorry.
My name is Shumit.
So Shumit, he pointed out that if we look at the very good point, if we look at the three-dimensional representation, none of these elements here are diagonal, right? So all I've done is I've chosen, right, I've written out H as I times this three-dimensional representation, where again, this should be a 2. And then I've diagonalized. I've just, so sorry, that was a little bit tricky. I should have mentioned that. So the good point, and it follows on to what I'm going to be saying now, and that is the following. What is important about the Cartan subalgebra? The important thing about the Cartan subalgebra is that all of its elements commute with one another. Right? What that means is when we represent these elements as n by n matrices on an n-dimensional vector space, we can simultaneously diagonalize all of the basis elements. Right? So you can think of the Cartan generators as the simultaneously diagonalizable basis elements in our representation. In this case, we only have one basis element and we can diagonalize it. And when you do that, you get 1, 0, 1. If you had chosen any of the basis elements and diagonalized, you would have gotten the same set of eigenvalues. Does that answer your question?
Yes, thank you.
And for anyone else, if you have, so one thing I want to mention is this subject can be quite confusing because you have an algebra represented on different representations, and then the eigen values that we're looking at, they sit in a root space. So there's lots of different pieces floating around, and it might get confusing. If that's the case, just stop me and slow me down. I'm happy to answer any questions. Okay, so back to what I was saying. The nice thing about the Cartan subalgebra is that all of the elements commute. And so when we represent them as, say, matrices on a vector space, those matrices can be simultaneously diagonalized. Right? And what that means in practice is we can find a basis for our representation space, our V, in which our basis elements are labeled by all of their corresponding eigenvalues, right? All of the basis elements act as eigenvectors of our Cartan subalgebra, and associated to them are the eigenvalues of the Cartan generators, right? So that means for a rank L, say, Lie algebra, any basis element of our representation can be labeled by L eigenvalues. And it's a very nice naming convention. As you can see, in the two-dimensional representation, you'll be labeling your basis vectors of V by half and minus half. In the one-dimensional representation, you'll be labeling them by 1, 0, and minus 1, and so on for higher dimensional representations. So that's what's interesting about the Cartan subalgebra. So what's interesting about the ladder operators? And again, I'm going to give some examples, and then I'll talk about the general case, and then we'll wrap it all together to make sure it sort of makes sense to you. Okay, so let's look again at our representation on SU2 of SU2 rather on V2. Right? So again, we can write out our basis elements of V in terms of this nice basis. And then it turns out that we can construct our ladder operators, E plus and E minus, in the following way, right? In terms of T1 times I plus T2 and I times T1 minus T2, right? And again, we can do this because we've extended our algebra to be defined over the complex numbers. And so don't worry too much about this form over here. I will show you shortly that these do in fact satisfy the properties of the ladder operators. For now, just focus on their form over here. And what you'll see is that these ladder operators in this nice basis are off diagonal. Right? So what E plus does is if you act E plus on this basis element, right, it'll map you to this basis element. Can someone tell me, are you able to see my mouse? Is that something that's visible to everyone that's listening?
Yes.
Okay.
Yes.
Okay, so that's important. so this E plus you can view it as a creation operator, which maps you from this basis element to this one over here. And if you act again on this basis element, you'll get mapped to the 0 vector. Similarly, this E minus will map you from this basis element to this one, and this base element will be mapped to the 0 vector, right? So you can view these ladder operators as mapping you between the basis elements of our representation. Okay. So just another example, so the 3-dimensional representation of SU2, so SU2 on R3, we can choose this nice basis here, and our creation and annihilation operators, our ladder operators rather, they map us between these basis elements. Right? One, the E plus maps us up, and E minus maps us down. Okay. All right, so this is actually going to be generally true. So if we have a look at our root equation, right, our product rule for our Lie algebra in the Cartenbar basis, what we find is the following. If we start with some basis element lambda and we act on it with our E alphas, then we're going to be mapped to some other basis element, right? And you can work this out for yourself in just a few lines. It's a very simple calculation. What you'll find is that the eigenvalue of this basis element with respect to the Cartan generator Hi will be given by lambda I plus alpha I. Right? So in other words, our ladder operators, they map us between our basis elements, and each of our basis elements is going to have a unique set of eigenvalues associated to it, right? Which are of the following form. Right? Now, the reason why that's interesting is that if we look at a finite dimensional representation, then it'll have, if we look at some basis for a finite dimensional representation, there'll be a finite number of basis elements, right? And so there'll be a finite number of eigenvalues associated with those basis elements. And so what you'll find is if you repeatedly act with our E alphas, you'll get to a point where there's some value here, lambda I plus alpha I, that doesn't sit in the representation. Right? And so what that means is there's some highest weight, some highest value, some highest element in our representation space. And we can use our creation and annihilation operators to map from that element to any other element in the representation. So the interesting thing about ladder operators is they allow us to fill out a representation. Right? So one element will be given by, for example, lambda with n of these E alphas written in front of them. Right? I hope that's clear.
Professor?
Yes.
Which special quality of the ladder operator just give the fact that I am not jumping of two states. I mean, from one state to -1 state to 0 state and 0 state to +1 state, which is, I mean, E alpha can get to -1 to +1, right? What's the point that it will always exhaust the vector space of mine?
So I'm not sure I understand the question. So let me repeat it and let me know if I understand. You're asking, how do you know that the creation and annihilation operators will exhaust the full list of eigenvalues?
Yes, exactly. Because I have just constructed E alpha by linear summation of the other two operators, right? So yeah. Why is it exhausting all the eigen bases? It's not jumping. I mean, there can be an eigen basis between 0 or 1.
Yes.
Right? How can I be sure that there is none?
So if you have a look at the form of this equation here, right? So if you look at this expression, so what this expression is saying here, this take it that this lambda, this is a basis element of my representation space, and associated to that will be the eigenvalue lambda or lambda I, right? If I have I Cartan elements, okay. So if you can check for yourself that if you act on lambda with E alpha, right, and you make use of this rule here, what you'll find is that you'll get, after very short manipulation, you'll have the same element back, but multiplied by some eigenvalue, right? Now, if you have a finite dimensional vector space, that means that it'll have a finite number of basis elements, right? And we've already seen that each basis element can be labeled by its eigenvalues, right? So what this equation is telling us is that if I start with some eigenvector, with associated eigenvalue lambda, that if we act with E alpha, right, we'll get a new basis element, right, with the corresponding eigenvalue, right? Now, by repeated use of the E alphas, what we'll find is basis elements which have higher and higher
lambda I plus 2 alpha I plus 3 alpha I.
Yes, and so on, right? Yes, and at some point, this will go outside the range of the eigenvalues of the representation. And you might wonder, how does that happen? Well, that happens when E alpha maps the basis element to the zero vector. Yeah, so this equation can be satisfied either when this basis element has this eigenvalue, or when this basis element is the zero vector.
Okay. But why not lambda I plus 0.5 alpha I? Why it's not there? I mean, how can I be sure?
How can you be sure?
I am getting lambda I plus alpha I, lambda I plus 2 alpha I. How can I be sure that there is no independent basis state between these two, that E alpha is missing?
The reason why you can be sure of that is because this equation here, right? So you know that the basis vectors are labeled by their eigenvalues, right? And you know that every time you act with the EAs, you'll get an eigenvalue plus some alpha, right? Now there are a few properties that tell you that these values have to take on very special form. So one of the properties is the following. So if you have a look at this equation here, right, this expression here, and you take the dagger of both sides, right, what you'll find is the following. Since these alphas are real, they're real structure constants, what you'll find is the following expression. Right?
Okay.
So what this tells you is that for every E alpha, there is an associated negative alpha, right? An associated E negative alpha, right? Which has a root here, which is negative of the corresponding root for the E alpha. Right? So in other words, for every eigenvalue, you have also the negative of that eigenvalue, or for every root, you have negative of that root. Right? So in other words, for every creation operator, you also have a corresponding annihilation operator. So this is the reason, for instance, that if you have a look at these examples, the eigenvalues sit symmetrically about zero. So here you have, for example, a half and minus half in the two-dimensional representation. In the three-dimensional representation, you have 1, 0, and -1. here, for example. Three-dimensional representation, the eigenvalues also sit symmetrically around 0. So you see that there's some restrictions as to what these values can take. Now, in addition to that, the Cartan subalgebra has to obey the properties of the Lie algebra, right? It has to satisfy these commutation relations. These ones here. These commutation relations put strict restriction on what the difference between any eigenvalues can be. The difference is going to be precisely this value here. Right? If you just so I recommend you take this expression and you work out as I've done here, and you'll see that the eigenvalues of any two representations always differ by one of these alphas, one of these roots, right? And so those two restrictions together restrict what you can expect in terms of your labeling roots. They're always going to be symmetric, and they're always going to be separated by these values here.
Okay.
Is that somewhat clear?
Yes. Yes.
So I highly recommend playing around with this a little bit and playing around with some explicit examples to get a feel for this, right? So in any case, where was I? So you can see for every creation operator, there's a corresponding annihilation operator. Just to write down some of the examples. So I gave you some examples previously, and I'll just condense them now. So for SU2, for the SU2 Lie algebra, we can write out the generators in the Cartenbar Basis as follows, right? And we can go ahead and we can check, and these do indeed satisfy all the properties that you'd expect in the Cartenbar Basis. So you can view these root equations as the adjoint representation of the Lie algebra on itself. So you can see this as being an eigen equation or a root equation, where here H is acting on E plus and minus, and resulting in the following expression. So here, in other words, the E plus and E minus are both eigenvectors of H in this adjoint representation, right? And the corresponding roots are -1, 0, and 1. Right? These are the roots or the weights in the adjoint representation. So what we can do is we can take this Cartenbar basis, and we can express the two-dimensional representation in that form, and we get what we previously saw up above, and again for the three-dimensional representation. Now, we could keep going and playing around with these roots, but a much nicer thing to do, which is what I want to do now, is we can express these roots in terms of a weight diagram. Right? So given any representation, we can express the representation space in a nice basis, which is labeled by the corresponding eigenvalues of the Cartan subalgebra. And so, for example, for the SU2 Lie algebra, we can express the roots of the two-dimensional representation as crosses on this one-dimensional line. Right? So the two-dimensional representation will have associated to it the eigenvalues half and -1/2. Right? The three-dimensional representation will have associated to it the eigenvalues +1, 0, and -1. So these are the roots of the SU2 Lie algebra. Right? These are the convention is that for any different representation, you can list the corresponding weights, right, or the eigenvalues rather, onto this plot. And so for any representation other than the adjoint, you mark them with a cross, and the adjoint representation you mark with circles. That's the usual convention. Right? So I've shown the two-dimensional representation, three-dimensional representation. The four-dimensional representation would correspond to all four of these crosses here. Right? And the zero-dimensional representation would just be a cross at the zero, right? The singular representation. Right? So let's have a look at a more interesting example. Right? So the Su3 Lie algebra can be expressed in the Cartenbar basis as follows. Right? So we have the the Su3 Lie algebra is of rank 2. So it will have at most 2 simultaneously diagonalizable basis elements, or simultaneously commuting basis elements, and we can choose them to be T3 and T8. Right? And then we can construct the following creation and annihilation operators using the following combinations. And you might ask, how do we choose these combinations? We choose these combinations by having a look at the structure constants. We go back and look at the Su3 structure constants. If you look here in the structure constants, there is no structure constant which has an index 8 combined with an index 3. Right? 8 always appears on its own without a 3. Right? And what that means is that Ti will always commute with, T3 will commute with T8. So I can choose T3 and T8 to be the basis elements for my Cartan subalgebra. Similarly, if I look at any structure constant, any of the structure constants that have 8 in them will have some pairings. So 6 and 7, 4 and 5, and so on. And this is how we choose our pairings down the bottom when we're constructing our Cartan basis. So this is how we choose our pairings of T6 and T7 and 4 and 5 and 1 and 2. So if you've not played around with these representations before, I'd recommend you play around with them and convince yourselves that they do in fact satisfy all the properties of the Cartan basis. Right? So in particular, the Cartan subalgebra commutes with itself, and all of the other generators can be expressed in these nice eigenvalue equations, right? In these root equations here. Okay, so what I want you to note is the following. If you look at, for example, this E1 plus, right? Then E1 plus acts as an eigenvector of H1 with eigenvalue +1. And it acts as an eigenvector of H2 with eigenvalue 0. Right? So we can write down its eigenvalues in the following way, +1 and 0. Right? These are the eigenvalues of the E1 plus ladder operator underneath H1 and H2. Similarly, we can look at, for example, E1 minus, and it will act as an eigenvector with respect to H1 and H2. So with respect to H1, it will have eigenvalue -1, right? And with respect to H2, it will have eigenvalue 0, right? So we can label these basis elements, E1 plus and E1 minus, in terms of their eigenvalues with respect to H1 and H2, the Cartan subalgebra generators. And similarly, we can do this for all of these ladder operators, E2 plus, E2 minus, E3 plus, E3 minus. And when we do that, we'll find the following root vectors, right? Oh, yeah. And what we can do, since these sit in some two-dimensional space, is we can plot them in a root diagram. Okay. So what's nice about these root diagrams is every single Lie algebra will have a unique root diagram, right? So this is the Su3 root diagram, right? But there's also an Su4, SO2, SO3, and so on. They'll all have their own unique root diagrams, and so we can use these root diagrams to classify our Lie algebras. Right? And what Dinkin diagrams are is they're a nice way of encapsulating all the information about these root diagrams in some nice two-dimensional form, right? Because, so Su3 is a rank 2 Lie algebra, right? Which means that all of its, for any representation the basis elements of that representation will be labeled by two roots, right? Some two numbers associated with the two generators of the Cartan subalgebra. But when you start looking at larger dimensional, Lie algebras, which are of higher rank, right? These root diagrams are going to be higher and higher dimensional. So they become unwieldy. What Dinkin diagrams do is they're a way of expressing all the information of a root diagram in two-dimensional form, right? And so that's actually the content that I wanted to introduce today in today's lecture. And I was planning on going tomorrow over the actual construction of Dinkin diagrams from the root diagrams. So I'm running quite a bit early. I was expecting actually to have quite a few more questions, but maybe this is a good time to make a pause and pick up from tomorrow, if that's okay with everyone in the lecture hall, or if you have any questions.
Professor?
Yes?
In the previous page, in the origin, there are two roots, right?
Yes.
The +1, -1, and 0 from the H1 first gives me 0, 0, 1, 0, 0. But here comes the other 0, 0 part from here.
Sorry, could you repeat the question? I didn't hear you properly.
I can get the fact where the two 0, 0s are coming from. First 0, 0 I can get because alpha for the H1 E1 plus gives me +1, 0, and -1. Then the 0, 0 pair comes from there. But the first 0, 0, where does it come from?
So you're wondering why there are two sets of 0, 0s here?
Yes.
Oh, so the way to view these plots is as follows. This is an 8-dimensional Lie algebra. So there's going to be 8 basis elements. And these basis elements are H1, H2, E1 plus, E1 minus, E2 plus, E2 minus, E3 plus, E3 minus. Okay, and so what you can do is you can view these expressions here as root equations, right? So for example, this equation here, right? I can view this as being H1 acting on, I can view this equation as being HI acting on HJ, right? So there is one root equation, which is H1 times H2 will be 0, right? That's associating the 0 eigenvalue. Let me say it the following way. This equation here, what this is saying is Hj is an eigenvector of Hi. And Hj is also an eigenvector of Hj, right? So just to be clear, H1 is an eigenvector of H2. And H1 is also an eigenvector of H1, right? So the eigenvalues associated with the eigenvector H1 will be 0, 0, right? Because it's an eigenvector of both H1 and H2. Now, H2 is also an eigenvector of both H1 and H2. And so it will also have associated to it as 2 0 eigenvalues. Right? These two roots here correspond to the two H's. Does that make sense?
Okay, I get it now.
Yeah, so the counting is for each one of these basis elements, including the elements of the Cartan subalgebra, you should have a set of roots, right? And so you just look at the root equation and ask, what are the, if I view any one of these generators as an eigenvector of the Cartan subalgebra, what are the associated eigenvalues? And if you ask yourself that question, you'll get precisely the root vectors that you see here down the bottom.
Okay, thanks, Professor.
Excuse me, may I ask
Yes?
him some question?
Yeah, sure.
Actually, though I'm from physics, so this Lie algebra I have worked with, but main problem, there are twofold problem I face with. One is algebraic pair that can be practiced and handled. There is a mathematical method. Could you kindly, one of the simplest possible example, could you kindly give some example in your own terms with molecular interpretation, physical interpretation? Any example, any of the example you feel suitable. You have been showing them. You have been giving more emphasis to the mathematical aspects of that. So is it possible? I don't know whether these examples are suitable here, but all are having some molecular interpretation. So is it possible now to give at least one example?
Yes. So I'll give one example. So if we go all the way back to the start. So you're happy with any physics example or use of these Lie algebras? Is that the case? Yes. Okay. So if you look at, for example, the classification of the Lie groups that we're interested in, and almost certainly you've come across the special orthogonal groups, right?
Yes, sir.
So when you're considering rotations in space, the symmetry group that you're interested in is the special orthogonal group. This is the group of rotations in some n-dimensional space. Okay, so for example, if you look at SO2, you can express the group elements in matrix form. There's a nice representation, a two-dimensional matrix representation, written in terms of I can't write it. I need a blackboard, but more or less you can express SON in terms of 2x2 matrices with causes and sines as the elements, right? And those matrices will correspond to rotations of some two-dimensional object in space, right? Now you can always represent those 2x2 matrix elements as the exponential, as the matrix exponential of some anti-symmetric real 2x2 traceless matrices. So that's one example of where this would show up. So for these special unitary groups, I'm actually going to give, so my very last lecture is going to be completely dedicated to physical applications. And what I will talk about in much more depth is how special unitary groups pop up in particle physics and high energy physics. And you've probably heard that physical theories have what's called a gauge group associated to them. So it turns out that for all of the forces that you see in nature, there's always associated to those forces some symmetry. And it turns out that for the standard model of particle physics, that's the model that describes nature around us, it has three forces called the strong force, the weak force, and electroweak hypercharge. And associated to those forces are three symmetry groups. So associated to the strong force is a symmetry group called Su3, and associated to the weak force is a symmetry group called Su2, and associated to the hypercharge is U1. Okay, and so so I'll talk about this in depth in my third lecture, but essentially, yeah, these you can think of these as the gauge symmetries or the local symmetries. You can think of them as the rotations in some internal space in particle theory. So that's another example. Is that the sort of example you wanted, or you wanted something more hands-on than that?
No, actually, you have given very nice explanation. I was enjoying it. But one thing, those examples you have cited, is there any possibility of giving some physical explanation of those equations? Some examples you literally brought, actually. You have been showing the mathematical examples. Your presentation was so nice. I was enjoying it. Actually, it was visualizing the whole story, and it's repeatedly also. It's very nice to see, listen this every time. But the examples you have been citing, from these, is it possible today to give some physical examples? Because you have been highlighting some of the very nice mathematical examples in a very systematic order.
Okay, so just so I'm clear, so you would want you want something like an explicit construction, or just listed like examples.
No. Some examples, because expansion time, that is not physical touch. The example you have been showing, you just give a brief touch, because that will be easy for me to interpret immediately the examples that you have been showing.
Yeah, so what's a nice example that I can give? So maybe I can talk a little bit more in depth about these special unitary groups.
Yes, sir.
Are you familiar with covariant derivatives?
Yes, sir. Little bit.
A little bit. Okay, so what you find is so when someone says that a particle theory has SUN symmetry, a field theory, for example, what that means is that your fields, so imagine you have some space-time and you have fields defined over that space-time. So those fields can be real valued. They can just be a number, right? They can be, you know, everywhere in space you attach a number that in some smooth way, and that's how you visualize a field conceptually.
Yes.
But a field doesn't have to be real valued. A field can also have, it can be matrix valued, it can be a vector valued field, right? So at every point in space you would have some vector, and you smooth those vectors smoothly vary across space. Now, we've been talking in this lecture about symmetry groups and their representations. So you can have a field that sits in the representation of some symmetry group, right? In particular, in the standard model of particle physics, when you say that a particle has some symmetry, SUN symmetry, say, what that means is that that particle, you describe it by some field, and that field is represented, that field is representation valued, right? So it's some, for example, at each point in space, you attach some n by n representation or some n-dimensional representation of your symmetry group, okay? And so the symmetry can either be global or local, and what it means to have a local symmetry is that the fields can locally, so the fields which sit in some representation of your symmetry group can locally transform under the symmetries of that group, right? And so what you say is that for the standard model of particle physics, your fermions, your matter fields will sit in certain representations of your symmetry group. Your gauge bosons, these are the force-carrying particles. They'll always sit in the adjoint representation of your symmetry group. Then you have scalar fields. They'll also sit in some representation of your symmetry group. And so this is what it means when you say that a field theory has some gauge symmetry. It's a little bit hard for me to give more of an explanation without a blackboard, because I'm trying to say things that won't be confusing. Is that helpful to you?
Yes, sir, that was fantastic. But one question more, sir, because there's time, so I can ask. So I'm asking you. It's a privilege for me to ask. Thank you. Actually, the point is this: why we are taking so much of trouble? Because that question sounds very odd, but so many days that has been in my mind that if we do analyze with Lie algebra, we are somehow dependent on the spectroscopy. So people may ask us that why we are going for that.
Sorry, what do you mean?
Why we're almost all the cases relying on the data from the spectroscopy? That is my work. Of course, people may do much advanced work, but what I have done so far, I know what I have done myself. We are relying on the spectroscopy results. Then why not to go for the molecular analysis? Why not to go for the spectroscopic analysis only? Why we go for Lie algebra? That can be a question. Actually, someone asked me this, and then I started thinking, and I was thinking this for quite a long time.
It's actually quite interesting that you ask that, because originally when people were playing around with group theory, they thought it was kind of a nuisance. You know, why do we need to deal with group theory at all? It seems like, you know, this, you know, highly mathematical sort of thing. But it turns out that when you're trying to describe physics at a more fundamental level, so for example, if you're dealing with electromagnetism, then the most efficient and compact way of describing that physics is in terms of gauge groups. Group theory gives you the most compact and nicest description of the physical world we see around us. So it's sort of out of necessity. So you were talking about at the level of spectroscopy. So by that I imagine you mean you're looking at the energy levels of atoms and that sort of thing. Is that what you mean?
Yes.
Yeah. So when you start, what you'll find is, as I said, there's a theorem called Noether's theorem that I'm not going to go into today, but essentially every force that you see, right, is associated to a symmetry. So as I said, the strong force is associated to Su3 in a way that I'll describe in my third lecture. And so what group theory does is it gives you, it is the mathematics that describes what we observe. And that's why it's interesting. You know, it's sort of like asking, you know, why do we need special orthogonal groups to describe rotations in space? And it's because special orthogonal groups are the objects that describe rotations in space. So when we're doing a high energy particle experiment, what we find is that the particles have sort of an internal space, and rotations in that internal space are described by, in the case of the standard model, these special unitary groups, just like the special orthogonal groups describe rotations in our extended external space. So that's why it's interesting. It's literally the objects that describe what we see in high energy experiments, like in particle colliders and that sort of thing.
Thank you very much, sir. It was very nice understanding. Though my question was very primitive, I know, but I have been struggling with something, so I put up the question, and maybe later we'll discuss about this. I have some more doubts, but not right now.
So if you have any questions that you want to write to me, I'm very happy for you to send me an email, and I'll try to answer any questions directly as well in that. I can also direct you to any reading that might be useful.
Thank you so much, sir. Thank you very much.
Hi, I have a question.
Sure.
So can you go to the last slide, please?
The last slide? Oops.
No. Yeah, this one.
Yeah.
Yeah. So going from the basis E1, E2 to up to E8 to this new basis E1 plus minus, E2 plus minus, and so on. This is a transformation in the vector space on which you are representing the algebra, right? So now, as you have written the new algebra in terms of H1, H2, and E1 plus minus, and so on. Yeah. So now we can see, no, the next slide.
Yeah.
The new commutation brackets. Yeah. So now we can see that here H2 commutes with E1 plus minus, and H2 commutes with itself, of course. So can we reformulate this whole thing in terms of H2 and E1 plus being the new Cartan subalgebra and draw the new root diagram in terms of H2 and E1 plus? Because these two also commutes and yeah.
So the answer, I suppose, is, well, first of all, there's a few things to say. So E1 is not Hermitian, right? So
oh, right. Yeah.
one thing I didn't give emphasis on is, so one of the reasons why you wanted to write out the basis in this form, right, is so that H1 and H2 are Hermitian, and that will give you real eigenvalues. But the question you ask is good, because there's not really any, you can find infinitely many bases that, there's nothing really that special about the bases that I've written down here. You can also find other ways of representing the Cartan subalgebra, right? You can find other combinations.
Yeah.
This is just a convenient one. I would recommend, if you're curious, to look around and see if you can find other examples. So a clear example is if we go back to the Su2 example. So we chose T3 to be our Cartan subalgebra. But there's nothing special about T3. We could have chosen T1 or T2 to be our Cartan subalgebra. Right? I've just made this choice here because it's convenient for the explanation. But it's a good question. There's usually infinitely many ways that you can break these things up, and it's just up to you to find a good representation.
Okay, thanks.
Shane, I just wanted you to show the next slide, please. Can you go to the next slide, the root diagram?
Yes, yeah.
Yeah. So there are, you see these 8 points, right?
Yeah.
The origin is doubly occupied, so to say. There are 2 pair of 0 zeros.
Yeah.
So this hexagon gives you 6 and the origin, that is 2, so it makes total 8. Now each slot means the coordinates of all of these points involves 2 slots, and one slot, the left slot corresponds to eigenvalue correspond to H1, and the second slot corresponds to the eigenvalue H2. Now if you consider the top pair of slots in the hexagon, then it seems they will be connected by, again, the Su2 ladder operators, right, in the half representation. And along the x-axis, it will be connected by Su2 ladder operators in the j equal to 1 representation. And the bottom one again back to half representation. Is that it?
So I'm having trouble hearing. You've got lots of noise in the background. But can I repeat your question and tell me if I've understood correctly?
No. Can you hear me? There's a noise background?
Yeah, it's very hard to understand what you're saying. But so you're asking about whether these objects fit in certain representations of the others?
Yeah, whether these horizontal points, they are connected by Su2 ladder operators in the half representation.
Yeah. So for example, if I've understood your question properly, if you look at this root diagram here, right? This root diagram here, and you look at these 3 roots here, 1, 0, minus 1, 0, and 0, 0. They will form an Su2 subalgebra, right? And then these 2 roots, for example, transform as a doublet underneath this Su2 subalgebra, right? In fact, this is what I'm going to be talking about next lecture. But yeah, you're right. So if I've understood your question correctly, and the generators of the Lie algebra map the basis elements into one another. So, so yes, for this to be a consistent root diagram, every single root, so for example, this one here, has to sit in a representation of any other triple of roots that appears as an SU2 subalgebra. Right? So what I mean by that is pick any line going through the origin, any line at all. So this one, or this one here, or this one here, right? And then every other root has to sit in a representation under that subalgebra. So this set of roots here corresponds to an SU2 subalgebra. So does this one here. And you can think of these roots, for example, this root here, if you project it down, will sit as a doublet underneath this SU2 subalgebra, where this is the doublet pair up here. Is this what you're asking about? It's a little bit unclear because I can't hear your mic very well.
No, it answers partially, but what I'm saying is that you can also think of the top two ones. For example, half root 3 by 2 and minus half root 3 by 2 as also a SU2 doublet, is not it?
Yes, that's true. That's true.
And the horizontal ones, minus 1, 0, 0, 0, 1, 0, that can be a triplet under S.
Yes, exactly right.
Another 0, 0 will be the singlet one.
Exactly. Yes, that's correct. So for example, in here I have I've highlighted here these three roots, this one, and this one, and these form a SU2 subalgebra. And under the action of this subalgebra, there's another root here, the second root. This acts as a singlet. These roots themselves act as the adjoint representation, or a triplet. And then these two here act as a doublet, just as you said, and these two here also act as a doublet. And that's something that I'm going to be discussing at much greater length next lecture. And I'm also going to be talking about Dinkin diagrams themselves. So this was just to get you sort of comfortable with root diagrams to this point. Is that what you're looking for?
Yeah, means this answers my question. But now the students, if there are any questions from the student side?
Professor?
If you have any question, please ask.
Professor, can you hear me?
Yes, I can perfectly.
I have seen, or it seems like that in particle physics, it's exactly like the octet formation, right? I mean, the pion sitting there -1, the triplet states, and there are cation and positive cation, negative cation. Exactly how does I can associate with the octet formation in this root diagram? Can you please say some words on that?
You're talking about the eightfold way?
Yes, eightfold way. I am talking about the eightfold way.
So I'm not. Unfortunately, I'm going to only say something stupid if I answer this question, because I'm not fresh on the eightfold way. So I won't be able to answer this question, but I can give you a different answer to a different question that might be satisfying. And that's the following. So the eightfold way, so what you're talking about is fermion representations. So in the standard model, SU3 is the symmetry associated to the strong force, and that means that the gauge boson, the force-carrying particles that convey the strong force, they will sit in the 8-dimensional representation of SU3, right? They'll sit in the adjoint representation of SU3. And what that really means is you have 8 gauge bosons, right, associated to SU3. Right? you can call them gluons, and you can associate one to each of the 8 basis elements that you see here, essentially, more or less. I mean, usually you wouldn't write them in the Cartan vial basis, but yes. So in that case, the basis elements are associated to the physical bosons you see in experiment. Is that, although I didn't answer your
No, I mean, how can I associate? There is a point, right? Just 1, 0, and they are the roots. Even if I have not discovered one particle, then and I can predict that there should be a particle. How am I positioning a particle in this way? There is always like 8 gluons, and obviously I can predict that there will be 8 gluons, but which gluon to which point, and what is the mapping between the points and which gluon? I mean, they're just root diagrams, right? And
yes, so the way it works is as follows. In your so what you'll have is you'll have some Lagrangian that describes the dynamics of your particle theory, right? And in this Lagrangian, you'll have a covariant derivative which has a connection term, and that connection term takes values in the Lie algebra, right? So when you physically write down the dynamics for your expressions, your gauge bosons will literally be an adjoint, or there'll be fields sitting in the adjoint representation of your gauge group, right? So that means you can write out any field as some coefficient, some space-dependent coefficient contracted with a generator of your gauge symmetry.
Yes.
So,
now I get it. Okay. So the SU3 representation always get the gauge fields will always represented by the adjoint representation, right? And
yes, and that's something I'll describe in the third lecture.
And the adjoint representation roots will predict the position of the 8 gauge bosons that I should have.
Yeah, so this root diagram so what the root diagram, so usually when you're so this is a little bit of a confusing thing that I should clarify this. So when you're dealing with a physical theory, so for example the standard model, you're dealing with a finite dimensional compact simple Lie group, right? And in that case, the corresponding Lie algebra is a real Lie algebra, right? So in other words, your gauge bosons, you can view them as being some real coefficient which varies in space, contracted on your generators, and there's 8 possible generators in the case of Su3. Now, this root diagram that you're looking at, this is like a trick. So we're taking that Lie algebra that you're interested in physics, and now we're complexifying it to start with, and so that complexification allows you to express the Lie algebra in a nice basis, which allows you to write out and draw these root diagrams, right? So in some sense, these root diagrams come from a bit of a trick, because you're dealing with a complexified algebra, and so you shouldn't really think of these roots here as being like particles or something like this. This is just a nice trick for classifying the Lie algebras. Is the way you should look at these root diagrams.
Okay.
But so when you're dealing, so if you want to ask a physical question, usually you're dealing then with the corresponding compact Lie algebra, which would be the small real form of the complexified algebra.
Okay, please.
Hello, sir.
Yes.
Thank you for the nice talk. I just want to ask one question. The rank of the
Saurabh, can you be a bit louder?
yeah, sorry. So rank of the algebra is, I think, equals the dimension of Cartan subalgebra. So for the case of Su2, we have rank 1, and for the case of Su3, we have rank 2. So my question is, my question is, does the rank 2 imply the number of dimension of Cartan subalgebra, or the vice versa? Means or the other way, means the Cartan, since the Cartan dimension of Cartan algebra is 2, so therefore the rank is 2, like that.
Yeah. So the rank of a.
So the question is, does the Cartan algebra comes first or the rank comes first? So the question is like that.
I guess they both come together. The rank. Yeah. So yeah. If you take a Lie algebra, you express it in terms of some basis.
Yeah.
The maximum, the dimension of the maximum. Well, so you express your Lie algebra in some basis, and the maximum commuting subalgebra is the Cartan subalgebra, and then you can ask what's the dimension of that Cartan subalgebra, and that will be the rank. I suppose the answer is the subalgebra comes first, and then you ask what the dimension of that subalgebra is.
Yeah, so since for the case of Su2, since the dimension of Cartan subalgebra is 2, so we said that rank of that Lie algebra is 2, right?
For Su3, yes.
Yeah, for the case of Su3, yeah, sorry.
Yes, exactly right. Yeah, that's right.
Yeah, okay, thank you.
Hi, sir. How do we find the Cartan subalgebra? Like, how can we know? Like, what is a subalgebra? I mean, how do we get it?
So to start, I can show you how you do it in a very simple example. So if you look at these structure constants, for instance, right, and you look across at this structure constant 1, 2, and 3, right? So what these structure constants mean is if you find a structure constant which has a combination, say 1 and 2, right? This tells you that T1 and T2 don't commute with each other, right? Because you've got a structure constant which tells you about their commutation relation, right? If you look through here, you'll find that there is no structure constant that has both a 3 and an 8 in it, right? Any structure constant that has both a 3 and an 8 in one of its indexes here will be 0. And what that tells you is that T1 and T3 and T8 commute with each other, right? And so the simple question is, how do you know what the subalgebras are? Well, you look at the structure constants and you see, can you construct combinations of basis elements which commute with one another? And essentially it's through construction for now until I give you a few more tools. You'll know what a subalgebra is essentially through construction. But we'll discuss finding subalgebras in the next lecture, actually, with a few more tools behind our belt. Is that an answer? Essentially, these structure constants tell you about all of the products in the algebra, and you can read off from those essentially how to construct commuting elements.
Okay.
That's not a very satisfying answer, but so later, as I said, tomorrow we're going to go through with a few more tools under our belt, and we'll look at subalgebras of the algebras.
Sure. Okay.
Professor, in this case, is it safe to say that because T3 and T8 in my Gell-Mann matrices representation, they are diagonal matrices, right? So
Yeah.
I can multiply the operators T3 and T8 and I will get just diagonal elements, just numbers. And T8, T3 will give me numbers, and numbers just commute. So I can safely take lambda 3 and lambda 8 as my Cartan sub algebra. Is it okay to say this?
That's one way of saying it. Another thing you can do is, given any matrix here, so say for example you look at this lambda 1, right? You can do a transformation on the basis to diagonalize lambda 1, right?
Yes.
And then you can ask, this is probably a better way of answering the previous question actually. So you can ask, is it possible to simultaneously diagonalize lambda 1 and lambda 2? And the answer is yes, right? You can find transformations which simultaneously diagonalize these two generators. And then you could ask, well, is it possible to simultaneously diagonalize 1, 2, and 6? And the answer is no. Like what you'll find is there's only enough freedom to simultaneously diagonalize at most 2 of these generators. And that's why the algebra is of rank 2. So it happens to be the case that lambda 3 and lambda 8 are already diagonal, and so it's easy to see that they commute and form a Cartan subalgebra. But you could ask, is it true that the Lie algebra really is of rank 2? Could I, for example, find a basis in which, say, lambda 6 or lambda 5 or any of the other ones is also simultaneously diagonal? And the answer is no. Like you don't have enough freedom to transform 3 or more generators so that they're diagonal. So in particular, if you look at all of these matrices here, these sit in a representation of SU3. So you can do SU3 rotations on these elements and transform them into diagonal elements using SU3 transformations. Yeah, so is that an answer to your question?
Yes.
Any other questions? Any other participant asking any question? Tomorrow, Dr. Farnsworth will have 2 lectures. So anyway, you will get him for quite a long time. So kindly keep prepared your questions so that in between 2 lectures you can ask tomorrow. Is that okay?
For me, it's okay.
Okay, so I mean, because I have to tell them, so if it's okay for you, then yeah, students can really do it. I mean, if they wish to do it. Yeah.
Yeah, I'm completely free for questions tomorrow after. And I should also say, I'm not. Did you share the lecture notes that I wrote up?
Yeah, I have shared with him. I have shared with him.
So I wrote those up very quickly. There might be mistakes in there, but in any case, if there's anything unclear.
Okay, so that can be verified.
Yeah.
Yeah, all the participants have the lecture copies of Dr. Farnsworth. So please go through them, and if you have anything you find unusual or you think that there's a mistake, so you can discuss with him tomorrow.
Yeah, so I look forward to seeing you all tomorrow then, I guess.
Yeah. And then we have Professor Ball speaking to us at 6 o'clock today. So now it is almost 5:40. So why not to take a 20 minutes break, freshen up and come back at 6. And if possible, you can also join. Or if you have other engagements, okay, you can.
I've got to prepare my talks for tomorrow.
Oh, sure. You should do that. So I think we stop here today, and we will see you tomorrow at 2 o'clock.
Yeah, look forward to it. See you all.
Okay.
Thanks for coming.
Thank you so much.
Bye.
Thanks.